So I'm Glenn Stevens at Boston University. I'm a mathematician, and my background is, I guess, in the Promise program, though actually it comes from a program called the Ross program, which I imagine people know as well. So I was a high school student in the Ross program back in 1969. Was there, I think, 4 summers altogether, 5 summers maybe. And then 20 years later, we started the Promise program at Boston University in an attempt to make sure that the Ross program survived Arnold Ross. And of course, Arnold almost survived us in the end, but that's another story. So Promise is a program for students, for high school students. I'll talk about that later on today. In our attempts to sustain the Promise program, we got involved in all kinds of other activities. Promise for Teachers is one of those things. So we started inviting teachers to the program in 1991. And that started us on a path of thinking about what it is that teachers really need and what we were doing. What does that have to do with what teachers do in the classroom? That continued for some time. In 2003, we were awarded an big NSF grant, a math and science partnership, about $10 million grant, to work with 7 school districts, 3 or 4 universities, and things like that. And this all was inspired by the original Promise program. So we kind of kept that part secret because we weren't sure how people would react to that. And so through the Focus on Mathematics partnership, we did a lot of other things. We tried lots of ways of working with teachers. We have actually quite a lot of experience. We've seen a lot of the obstacles that people will see when you talk to administrators. When you say some administrators, I would be tempted to say almost all administrators are going to cause trouble. It's okay to volunteer, but they don't want people come in and running the show, and one can understand that. Okay, so let me just talk about Promise for Teachers. So the question then that we had to think about was, what is it exactly that we would call effective teaching? That's our goal, after all, in running a program for teachers. And so here we have Bill McCallum talking about what you have to do. You have to look at students, paying attention to students. There has to be some good mathematics in there, and they have to be connected to one another. And that part of connecting to the two is not trivial. Okay, and then the question is, how we do this depends on what we think how students learn and what we think mathematics is. And I want to emphasize that I don't think there's a uniform view of what mathematics is, and I think that's part of my discussion. Okay, next, there we got it. Okay, so beliefs about students. First of all students can achieve at high levels. Students can enjoy doing mathematics. I've been talking to the choir. I know that you guys all already believe that, but I normally give these talks in other places. So effective teaching requires insight into how they think and how they learn, and this is all students. Not all students do learn the same way. What's the meaning of the student question, and how do we develop strategies to help them do that? Okay, now, beliefs about the nature of mathematics. The first thing I want to really emphasize, it sounds silly, but mathematics is natural. This is maybe the key thing. There's a lot of stuff on that slide. But mathematics is natural. I mean that in 2 ways. One, it's natural for people to do mathematics. And 2, mathematics is part of the natural world. It's not part of us. It's not something that we invent. It's something that exists. I'm just telling you my particular view, and I know there's not uniform agreement. Mathematics exists independent of us. Experience precedes formality. In other words, the roots of mathematics are not in the definitions and in the formal actions that we take, but rather in the experiences that we're trying to understand by going through those processes. Things like that. Okay, so next slide. Okay, we can just go further. Hit the next slide. Okay, so what do we have to know about mathematics? And so this is, the previous slide was about everybody's interested in what teachers need to know, and so here's our view. They need to be able to examine the entire mathematical enterprise, be able to see the whole thing. as a coherent body of knowledge, as a way of thinking about things. And that means they need experience of doing mathematics, grappling with problems, learning how to build intuition. Intuition isn't something one's born with, it's something that one learns how to build. Developing theories, becoming completely absorbed in mathematical activity for sustained periods of time. So these are examples of experiences that people need. Okay, I think this is Arnold Ross speaking about what we look for in a teacher, and his point is that it's not just one thing, it's the entire intellectual outlook, and he emphasized that this had more to do with things outside of mathematics, as much to do with things outside of mathematics as within mathematics. Overview, this is just I want to point this out. This is really an odd slide to put in this particular spot, but I think it's relevant, so I'll mention it. There's the Common Core standards. Have people seen those? Okay, nobody's talking about them that I've heard, but those are, I think, really, really important things right now for this group to be thinking about, because the standards for mathematical practice really fit into the kinds of things that people do in math circles. And so it's an opportunity for us to maybe do something meaningful. Next slide. This slide is important. It expresses something that, back one slide. That one. Arnold Ross. If there's one slide that I would ask people to read, it's this one. This is a quotation from Arnold Ross. It has been observed that every human activity experience comes first. And as this experience grows, the need for communication motivates the development of language. Experience first, formality second. Sadly, back. Sadly enough, in our classroom practice, we place language first and experience second. We worry about what we should say in order to help the student understand. There's a teacher-focused kind of thing. What do we say to help the student understand? By this we mean to provide the effect of experience through the use of suitably chosen words, and not unexpectedly the effect is at best a very pale image of the real thing. The thing that I just want to say that for me this is striking because I don't remember ever hearing Arnold say this. I spent 5 summers in his program. I'm virtually certain I never heard him say that. Nevertheless, 10 years later, 20 years later, this was very, very much the centerpiece of the way that I felt about mathematics. So the experience that he designed for us to have in that program somehow communicated this point of view. It's only 30 years after the program, in reading his stuff, that I found this quote. Okay, next slide. Okay, next slide. I'm just going to go a little faster. Hold on. Different types of mathematical experiences, that's what we're talking about. So in the various programs that we've run various types. They fall into what I think of as 2 categories. Immersion experiences, where the teacher or the student or whoever immerses themselves in doing mathematics, solving problems, developing theories, thinking for themselves, becoming independent over a long period of time. And then there are more school-based activities, which are closer to the math circles, but still not quite. We run study groups for teachers in the schools, which are like teacher math circles. I put teacher math circles there just as a reminder of what it's like. But the point is, they happen in the schools. We've been doing them for almost 10 years now. They've been extraordinarily successful in some schools, and not so successful in others, and the difference, I think, can be attributed to the difference in support we get from the administration. It's always after school, which I think is a bad thing, but that's the way it is. Okay, next slide. Typical features. This is also an important slide, but I have to go quickly through it. I emphasize the ideas of acquiring taste for hard problems. The role of experience. We really do believe that mathematics has an empirical basis. And the second one from the bottom, questioning answers. We try to stress in all of our programs the importance of asking questions. And we try to say that's much more important than the issue of answering questions. Answering questions, you just answer the question. You have to do something with it now. And a real mathematician is always coming up with new questions to follow up on the preceding question. And it goes on and on and on, and that's how we generate new ideas. And then this last one is also important, this idea of low threshold, high ceiling, because we're very involved in the process of trying to get everyone involved. And that means that the problems that you give people have to have some basis. First of all, by relying on empiricism or experience, everybody can have experience. So you start with easy things that everybody can at least experience, and then build them up into more theoretical things over time that not everybody will get. Next slide. That's pretty obvious. Next slide. Okay, we run seminars during the year. Is my time up now? Probably pretty close.
It's getting a little close. Why don't we say something about PCMI? PCMI, Park City.
Okay, it's not PCMI, it's Promise.
Oh.
We've been doing this since 1991, and we engaged with PCMI in 2001, I think. But we've been doing it long before that. We just became connected as one of their professional development outreach groups. We run, but we've been doing it before. There are 5 full-day academic year seminars that we run for teachers who go through the summer program, and they come in for 5 days, basically. They spend the whole day with us doing mathematics. And if we just keep going, you'll see an example. Next slide. Lots of stuff. Next slide. Here's an example of what we did on December 9th, 2011. Okay, this is typical of what happens. One slide back. Go back. This is the summary of what happens. There are 2 parts. There's the morning part and the afternoon part. The morning part is just kind of informally talking about what's been going on, and then talking about things that teachers have done with their students between then and the last seminar. So they give presentations and interesting things like that. And then in the afternoon, we introduce some mathematical topic, which is, it varies from time to time. And I'll just go quickly. You can see what the examples are. Next slide. Here's an example. One of our teachers said, in how many ways can a positive integer be written as a sum of consecutive positive integers? This was a variation on a very well-known problem. And so we started, everybody did examples. They did a lot of computations and looked at the data, and the data is sort of reproduced down at the bottom, but it runs down. And there are some surprises in the answer that people will notice. It's multiplicative, it's a multiplicative function. And so they study it for a while, and after a while they realize why, and they come up with explanations for that. Next slide. Here's a discussion. Somebody asked why this weird stuff with taking square roots doesn't work out quite the way you think it would. So we talk about that and the importance of giving clear definitions and defining functions precisely, things like that. Somebody from Los Angeles who flew in just for the seminar to Boston talked about her experience in the PCMI program the summer before, where she'd been doing some topology. Go on. And then we talked about generalizations of the Fibonacci sequences, so linear recurrences. And here's just an example that they spent quite a bit of time on trying to understand why what they were seeing happened. And I'll leave it. I'm sure people will look at that and we'll see what's happening. But it's very interesting and unusual for these teachers. I think that's my last slide.
Jason.
Sure, okay.
Can we switch to the
Hi, everybody. Am I going to go? I have no slides. Oh, perhaps I'll stay. Good morning. My name is Jason Ermer, and I am at UT Austin. I thought that was going to happen now.
Yep, you can, wherever you like. Focus on you.
How's this? Wonderful. Down here. That's right. So I'm at UT Austin. I work with the program called UTeach, and some of you may be familiar with that. We're secondary teacher certification at UT Austin. So I'm a former middle school math teacher, and I work now with pre-service math and science teachers And I've been lucky enough to teach some classes for future elementary school teachers too, which is exciting. But when Dave proposed this panel, and the thing that he just said in the opening about how math teachers come to a math teachers circle, I work with the Math Teachers Circle of Austin. We did our summer immersion in 2010, I think. We went to Palo Alto and got the spiel in 2009. And since then, we've grown to about 20 or 25 teachers who are coming regularly, which is a really great group. But we've heard this thing about, I'm doing these problems in the teacher circle, and then how do I make this transition back into my general middle school classroom? Sure, with really gifted kids, they could maybe do some of these advanced problems that are challenging for us as adults here in the teacher circle, but I don't see how I can take this back to my general classroom because of the level of the problems sometimes, but also because anyone who works with public school teachers knows, as much as we may wish it to be otherwise, that the tests that are happening at the end of every school year are driving a lot of what happens and the pressures that they feel to cover whatever they feel they need to cover and what other people tell them they need to cover by a certain point. And it's hard for them to imagine bringing in what feels like an enrichment activity when they know they've got a ton of stuff that they've got to cover anyway. So the thing that's been very interesting for me to think about is what problems have we been doing in the teacher circle, or what problems could we do in the teacher circle that have under the hood the middle school mathematics. So it's like Glenn was saying, a low threshold but a high ceiling, where the low threshold is middle school low, right? So that the teachers can get into it and then push the ceiling as far as we want to push the ceiling, but then middle school kids could get in on the low threshold too. And my classic example of this, you know, the locker problem. You know, the hallway with 1,000 lockers and the kids come in and the kid K changes the state of every K locker, starting with locker number K, whatever, okay. It's a fantastic problem. A challenge for anybody, I think, who sees it for the first time. Under the hood, it's all factors and multiples and, you know, prime numbers and square numbers and parity, and it's all middle school math under the hood. And I think that that's a great example of a problem that we've done in a teacher circle that could very easily become, you know, the opening activity in a 6th grade number theory unit, or, you know, with 7th graders talking about those same concepts. Anyway. So what I've done, my contribution has been to the panel here, has been to put together a document that I have not made copies of, but which we can put on the website, or if you, I can share my email address and you can ask me for it. But I've gone through and thought about the problems that we've done, and I've tried to pick out the problems that I think are the ones that most directly connect to the sorts of things that middle school teachers are doing in their classrooms. And I haven't shared this with the teachers yet because I just have prepared it for today, but I think we've actually done a fair number of problems that have things that really connect directly to what middle school teachers are doing and what middle school kids would need to be doing. And although the problems that challenge the teachers as adults with some really advanced and interesting, challenging mathematics, we've also done problems that can have the high ceiling and the low threshold. And so I've tried to pull out some of those. Those were my words. You know, Glenn said it better than I could. That's what it is, right? That it's about getting the middle school kids in. So that's what I've got, and that's what I'll share, either electronically or on the website, however we want to do that. I guess those are the same thing. And so that's my thing, and we can talk about that if you've got questions or ideas about that. But I'll pass the baton so that other people have time to speak.
Emily McCall.
Can we do Sage now?
Yes, we can do. Sage Moore.
Odd here because someone's up all over the screen. It's disconcerting. So my name is Sage Moore. I teach at Skyline High School in Oakland, California. It's an inner city public school, comprehensive, 1,800 students. And about a year ago, but actually with a Math Circle support in the Bay Area, I started, I think, 3 years I've done the Math Circle for Teachers Conference during the summer, and occasionally go out to the San Francisco Math Circle for Teachers organizations meetings, which has been really wonderful. For me, it took, there was a little bit of a barrier to getting the Math Circle started in my school, for me to take that step. And part of it was, although the materials that I've gotten and the experiences I've gotten through those different kinds of meetings and conferences, etc., was wonderful. There was a step of going, feeling like I had enough knowledge really to bring it out there into my classroom. And so it really took having a mathematician who said, yes, I'll help you out. And that was wonderful. And at that point, we were able to start and go on. One of the big problems with maintaining this and bringing it more and making it more as a kind of integral part of what happens in my classroom and the classroom, the other math classrooms in my school, is really to change the culture. Like you guys have spoken about it already, really. And part of it is understanding what mathematics is about. I came to the realization that yesterday that we all have such strong opinions about what mathematics is and what's the right way to teach it. And this includes even people who think they're awful at mathematics. So you'll have every administrator thinks they know the way to teach it. And as math teachers, we get this imposed all the time. You have to teach to the standards, you have to do this, you have to post learning targets, you have to do I do, we do, you do. And and that is a big, huge issue. So there's this this difficulty of really bringing this in that extends well beyond the teacher and the students, but the district, the administrators, etc. So what else can I add and say here? Another difficulty too is materials. We don't have materials. I don't have materials. I can't pick up a book and say, oh yeah, this is great, I'm going to use it, I'm going to copy this, and I'm going to use it. I don't have that anywhere. I pick and choose here and there. I've slowly accumulated different things. Some of the work from the Math Circle activities is great, but I almost always have to alter it in some way or another. I don't have the breadth of experience in mathematics of always knowing that this would be a really particularly good problem for this particular area that I'm working with for things at the moment. And so that's a big difficulty too. The Math Circle on the Math Circle in the Box book is great, but it's not classroom ready. You can't hear me? No. Should I stand up?
Yeah.
Please.
Help.
Okay, I'm sorry.
Use your teacher voice.
Right, it's my teacher voice. Okay, this is not 9 in the morning on a Sunday, it's classroom. Okay. Yeah, that actually projects, they can hear it better here too. Okay, sorry, so what I was saying is I lack materials. I need stuff that's ready, right? And I've collected a few. I need stuff that I can take, I can look at it, go, great, photocopy it, and use it right away. I need rubrics to grade it with. I need all that kind of stuff, because all that stuff takes so much time, and we are stretched so thin already. And sometimes when it says, okay, let's go ahead and do this in your classroom, it feels like you're being asked to do one more thing. And so if I can see a lot of my colleagues, not only is there a fear to interact with the mathematics in a way, there's a fear perhaps that they don't know enough, but it becomes this overwhelming task. And I think that, is true also probably of administration and districts and everything else. So I see the Common Core standards right now is really exciting. And I think it's either going to be disastrous or provide this, really fundamental change. And I see right now that there's this little window of opportunity that would allow some kind of real cultural changes to happen in the classroom. And part of it is going to be how useful can the mathematics community involved in this become for the district and the administrators. Because right now I see them developing curriculum or trying to develop curriculum, and they don't have a set of problems. And they're oftentimes not even asking the right people to come in and help. I mean, all of our textbooks suck. CPM is probably, you guys know CPM?
Connected math.
No, it's CPM. It's probably the closest, and I use it all the time. And even that I have to take. I have to try and see if I can photocopy and retype it, and it's like, it's arduous.
What's
but
CPM stand for?
College Preparatory Mathematics. So they've got some really good stuff, they've got questions, but that's the closest it is. But you can't get, like, I got a bootleg copy, okay, I got a bootleg copy electronically of the Algebra 2, there's no money for this stuff, I can't ask for it. And so, so these are some of the dilemmas that we deal with in the classroom right away. I'm really excited to hear about this low threshold, high ceiling, because I really believe that if we do this right, it will include all mathematics, not just the so-called bright ones, bright students. We include all students. And I've seen that happen a lot in the Math Circle. The one I'm running right now, I really try to court underperforming students. And it's pretty exciting. So I have students that are A students, but I have students that are D and F students too that come in there. And not necessarily struggling with that, I'm just talking about underperforming. You know, we know they can do much better than they're doing. And it's really exciting to see these kids get together, work together, and you can walk in there and you can't tell the A from the F students apart. They're equally engaged and they're equally contributing, and it's pretty exciting. Yeah, so my big, thing that I want to get across is we need teacher materials. And the teacher materials should have an aspect that is assessment in it too, because that's another big part of it. And,
Thank you. Emily, how would you want? Or just
Sure. I'm gonna stay seated, but I'll project. Can you hear me? Can you hear me in the back? Yes. Okay.
Only when you project.
Only when I project. Okay, is that all right?
Yes.
All right. So my name is Emily McCullough. I'm a high school math teacher at Mission High School in San Francisco. I have a BA in mathematics. I studied at San Francisco State University, which is where I got introduced to the San Francisco Math Circle. So I've been involved there as an instructor, as a math circle leader for about 5 years now. I also, when I have time, because teaching really does take all my time, I try to lead circles whenever and wherever I can in the Bay Area. I'm highly involved. Well, I try to be with the Oakland Math Circle as well. So I guess just what I want to say is that in the 2 years that I've been teaching, I have had a really hard time bringing what I'm going to call math circle teaching practices into the classroom. I think a big part of that does have to do with the culture of learning. My students come to me, they're already 14, 15, 16, 17 years old. They've been students most of their lives. And they're used to certain teaching styles or learning styles. And the activity that Jason was talking about, the locker problem, I've run that in math circles. I've run that in math circles with 3rd to 6th graders, with middle school students, with high school students. But I think that a big part of that activity is talking about the why. So, you get the kids to do it, and, the first, you find out that all the square numbers, I believe, all the perfect squares are open, or all the perfect squares are closed. But the big question really is why, because as mathematicians, we know that, okay, well, once we figured it out, the big idea is not, oh, all the perfect squares are open. As a mathematician, what I want to know is, well, why are they open? What can I learn? And so I think the first thing is to get my students to ask that question. Are they curious about that, or are they just satisfied that they have the answer? And I found that more of my math circle students they're like, why? Like, what is it worth? Let's look into that. But I don't know if I've been effective at all in getting my students in the high school to ask that question why, to be curious about that why. Or even if they have that question, to dig deep into the mathematics and talk about it. Then the second thing is, okay, so we can have a discussion. I can lead that discussion and help them, lead their thinking to what we should be thinking about, what kind of questions maybe we should be asking to get at that result. Let's look at divisors, let's look at factors. But I think the change is that we need to get the kids asking those questions themselves. And we could make, I would be so interested to see in what kind of curriculum you're developing and what kind of classroom-ready lessons we can get. But I think the big change is not, or I think what we need more than the curriculum, because there's so much curriculum out there, and it's true, some of it's good, some of it's horrible. Sometimes access to the good stuff is really difficult. Sometimes knowing what's good is really hard, or you have a lesson plan, but you have no idea how to teach it, how to run it. But I think the culture in teaching and the culture in learning is what really needs to change. And I'm really optimistic about the Common Core standards and the mathematical teaching practices. And I'm hoping that that whole movement will help align math circle teaching practices with secondary, elementary, or primary and secondary teaching practices. But I'm a math major. I'm an aspiring mathematician. I know what I want to do because I do it in math circle, and I'm getting better at that. But I have not been effective in making that happen often in my classroom at all, because of this culture of learning, because of the students I'm getting. I have not been effective in teaching 125 students a year how to think like a mathematical thinker, because they're not coming in with that, and that's a big shift. And so I think we're heading in the right direction, and again, I'm optimistic about the Common Core and how that will change the way that our students think what mathematics is, because I think that that's sort of a big part of it.
Susan?
I'll try and stand. My name is Susan Shaw. I'm a middle school math teacher in Colorado. And I first attended an immersion summer session with Pikes Peak Math Teachers Circle, and found myself completely overwhelmed in a group of people with challenging problems, and started noticing how I was looking at what other people were doing so that I could get a start on how to solve these problems. And I became aware of how some of my students might feel as learners in a challenging situation. And that was really a healthy experience for me. And I came away pretty brain drained at that point. We worked on some lesson plans during that immersion time, but I didn't really know where to start, because this was, to me, a very overwhelming experience. Very positive, but just so new in my paradigm of learning. Through that circle, we met about once a month in an evening session for 3 hours, where we'd have a speaker, continue our learning, and then we would present lesson plans that we had tried with our students. And although it was good, many of the lesson plans I didn't feel confident that I could use those lesson plans with students in my classroom. It was nice to have a bank of lessons, but I walked away going, nah, that wouldn't work, and I just didn't feel confident in what I was taking away from other teachers' lesson plans. After our state exam, I decided, okay, it's my turn to present a lesson. I guess I should try this. And I did my first lesson, and the students in my class really loved it. And I was like, wow, this was fun. And it wasn't a hard day of teaching, and the students really liked it. So I kept trying it about once a week, and the students were like, wow, that was really fun. Why can't math always be like this? And I began to think it was sad that I had waited until after our state exams to do this, but I didn't have a comfort level in how to teach this or how to do this. I didn't have the self-confidence at that point. I joined the Rocky Mountain Math Teacher Circle, and they taught it, or their circle was a little bit different, and I really liked the networking that went on at the tables and talking with other teachers, and it was a different kind of circle that was also very helpful. And over the course of the summer, I became committed to running a circle in my classroom, because I saw the engagement of my students at the end of that year. And I came in, I work with a lot of at-risk students, like they get dumped in my room. And I love them, but the challenge is how to engage them in math. And I take a survey at the beginning of the year, what are your feelings about math? And they all say, I hate math, I can't do math. And so my challenge was how to engage them in mathematics. And I also noticed that on Monday mornings, they came in sleepy from the weekend. So most of them would have their heads on the desk. And so my thought was, okay, I'm not a morning person. I don't like teaching on Mondays. So let's have fun on Mondays, and let's do problem solving. So we engaged in problem solving Mondays. And from the professors at UCD, I kept hearing them not call it problems, but challenges. So your challenges. And I began to use that word with my students rather than let's solve this problem. We have a challenge today. And for whatever reason, sometimes the vocabulary meant a lot to them. So, oh, okay, we have a challenge now. I started with Jim Tanton's candy sharing activity. So just having candy was an enticement to engage them into that problem. They all thought they would get candy if they participated, which they didn't, because they had to use it the rest of the day for the other 180. But it was an exciting thing. I didn't have an answer to that problem. I hadn't worked it out, so I became teacher as learner with them. So that was also an engagement to them. Oh, let's all work this out. I wonder what the answer is going to be. And that engaged them a little bit more, just to see me learning with them, and we were a togetherness kind of thing. So it became creating a culture and climate of problem solving together. The students got excited about Mondays, and as a matter of fact, a number of my students have to go out to at-risk services as an additional period, and I kept getting feedback. They love coming to your problem-solving Mondays. They love coming to your problem-solving Mondays. You can't stop that. My problem was, how was I going to meet my curriculum on the state assessment?
Your challenge.
My challenge was to, yeah, that was my challenge. Luckily, I have a principal who was a math teacher, and I told her this was my commitment. She's seen various professors coming in to help with my class. She's actually come in and watched as some professors have helped do my problem-solving papers. She's been curious about the outcomes and how this is going to be. I am curious how my state exam results are going to look this year, because I am not hitting all my curriculum. But my thinking was, if I can engage the students in problem solving so that they would persevere, and if I could ensure that they had some number sense, could they figure their way out of a problem on an assessment? I think my greatest results are seeing them engage in one problem. They will come in and say, I can't believe I worked the whole period on one problem. They will come in telling me about their exciting math experiences. I went to a math thing, and I'm seeing a change in attitude about mathematics. I'm seeing a change in their ability to engage in a problem. A lot of them, we will not finish before the end of the period. And I want to teach them it's okay. Maybe you're interested in it and you'll go home and keep working on it. Sometimes we just can't finish it in our class period. And they will come back to me and say, is this the right answer? Is this the right answer? And I'll send them back out with another question, and they'll go back and work on it. And that's the exciting thing about bringing it into the classroom. My concern is, again, not having challenges that I'm sure of. So this has been a year of trying different things. I've been relying on Solve This. I've been going through the Enrich website, trying to get different challenges that are appropriate. And it's helpful not only to have the challenge, but follow-up questions that could be asked that are helpful, and then, of course, the solution if I really need it. But those things, to me, would be really helpful in saving time and knowing what is going to work. At one point, I had such a fear I wasn't going to get through the curriculum that I needed to get through that I started integrating the problems that were related. For example, if I was doing geometry at that particular time, I'd try and inject a geometry challenge on Monday, and they would tell me I couldn't have that challenge. And I'm like, why not? Well, this isn't a problem-solving problem. I'm like, but it is. But for them, it was kind of it's middle school, obviously, but the dilemma was I had to have something different than what we were studying to make them really enjoy it. So the lesson I've learned next year is I'm going to change that paradigm a little bit. Ms. Shaw, this is not problem solving you shouldn't be teaching this today. You know, this is not problem solving Monday. And
Like it's just geometry.
yeah,
It's not a
it's like,
problem.
yeah, it's not a problem. And I'm just, so I have to figure out a better way to work that out.
Well, just teach the geometry while you're doing algebra.
That's what I'm gonna have to plan ahead so that they're doing problem solving ahead. But these are just little experiences that I've learned about, and I love it. I just wish I had more time for it.
All right. I think we'll let Florence say some words, and then we should have some discussion amongst the group. And so, can we switch to the computer slide? How do I do that? So. Will it continue to record, Florence? Why?
You want it all in here?
Laptop.
Oh, yeah, it is.
Oh.
On the projectors.
Ah, there we go. So,
You want it on all?
Florence is, yes, on all screens, yeah.
I'm going to stand up because I have a small, high voice. There we go. It's
Geostationary orbit.
It is a little too high, isn't it?
Nothing looks down on the Washington Monument. I promise you.
My critical thinking is I live in Washington, D.C., and some years ago, I was teaching high school here, and it was pointed out that there's a lot of math. There's a lot of math on the mall in Washington, D.C. And so here we have a picture of the mall. I see most of you are looking up this way. So that will show. So this whole thing is the mall from here to here. And this is Pennsylvania Avenue. You notice it comes in at a diagonal. And that's one of the exciting things about Washington. It's laid out as a grid with these great wide avenues named after states. And every time two states meet, there's supposed to be a monument. And for the most part, there are. And what I'm going to do is take you on a short walk called Math on the Mall, which has been taught as a after-school program at George Washington University for middle grade kids, strictly finding problems out there on the mall and then solving those problems. I'll only give you one of those. My idea of this talk, which was suggested by Dave, was to show you how to use your natural environment to create an exciting way to do mathematics. On the other side of the mall here are museums, and I'm going to talk about this one first, which is between a straight line and a diagonal, east-west line and a diagonal coming in. This building, and then I'll talk about this building, and then I'll talk about this building, and so forth, and I'll end down here. If you'll tell me when I have exactly 2 minutes left, okay? Because if you really took this tour, it would take 8 hours, and that's walking. And it is online. It's called Math on the Mall, and a friend of mine and I, Fred Rickey, he's a retired professor at West Point, wrote this many, many years ago, and then it's been picked up by other people. American Indians have math in the forest, and there's math at Niagara Falls, and so you're actually doing math as you go around in your own environment. Okay, next slide. Front of the National Gallery of Art, which you may not have seen, but that's the building that's squeezed in that special trapezoid that was created by the design of the city. And so the architect, a Chinese architect, I.M. Pei, had to put a triangular building in there. You can see the base of the triangle there, and back in the distance up here is where the triangle finishes. And then over here is a separate right triangle. And if you look right here on the edge of this right triangle, so many people have come up and touched it that you have what you might call a normal curve. The tall people with their greasy hands, and then the little short people. Because you can look down the straight edge, one side of the right triangle, and look down the hypotenuse. Only place in the world you can do that. Okay, the next slide. This is the design of the building. You can see it's all isosceles and right triangles, and they're a ratio of 1 to 1.5, which is fun and very easy for kids to see, or teachers too. Okay, next slide. That's just demonstrating where that is in that trapezoid on the right-hand side, okay? And there, again, is a slide, and you can now see the right triangle way over here on the right separated, and here's where the grease marks are, okay? And you should do it. If you go inside, it's all isosceles triangles again, and then there's this great hanging mobile by Calder. It was hung up there in 1982. Calder was an engineer, went to St. Stephen's Institute in New Jersey, and then began making these mobiles, which is a great thing to do with kids because it helps them to understand, and teachers, it helps to understand lots of things. So in order to make this, he just sort of had to work at it in great engineering because it weighs many tons, okay? And there's the simple way to understand a mobile. Next slide. And then it gets more and more complicated. So again, your geometry, this would fit right in because you have your ratios. And then, all right, next slide. If you go outside, you can see this tiling here. And if you look at it with great care, you can also be doing some geometry. Next slide. It's all tiled, that whole plaza. Next slide. And there is what has happened. The figure on the far right, almost an Arbellos, is made directly from the square on the far left by slicing the two arcs and then putting them up on the top. So take these two arcs and put them up here and you get the shape. Okay, and again, the tiles all over the city are absolutely magnificent for doing classification in mathematics. Okay, next slide. And if you go to the outside outdoor sculpture garden at the National Gallery, you will see this magnificent sculpture by Saul LeWitt, who made it in his head and then wrote down some specifications, and the builders then just build it. So again, it's very fun, and the teacher who created the Math on the Mall that's on the web has a nice exercise, having the kids figure out how many of those bricks must be there to make that happen. Okay, next slide. And that's one way to do it, by counting them, and then beginning to see the differences as you go along, being able to generalize. All right, next slide. Aha, this is a pretty remarkable piece right there, and I just have the number here. It has 15 extended octahedrons and 10 tetrahedrons. It's called Moondog, named after a blind poet in New York City, but it's an extraordinary piece of mathematics that you can walk inside. Okay? And this is the great Museum of the American Indian, which, if you've never been there, you should go there. It's the best place to eat in Washington, in their cafeteria by far, because it's set up that different Indian sections of the North and South and Central America have different food stations, so you can get food from Maine or food from Mexico and so forth. You'll notice the way it hangs over, a wonderful terrace where there are planets embedded, designed with the solar system in the plaza. And the museum asked me to do a Math on the Mall, Math in the Museum for them, so I wrote that book for them. And next slide. And here is an architect's plan for those cantilevers that you see hanging way, 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 way out here. And again, it's a magnificent mathematical problem, and both kids and teachers love to work on it. And you can take a deck of cards, as you probably know, and go out. But next slide. It turns out that just a couple of years ago, this is 2009, this was published in February, at the joint math meetings, it was announced that there was a better way to make a cantilever than using the harmonic series. The harmonic series is doing it this way, but it's possible to extend it even further. And that magazine, that's published in Science. So if you just put in Science and hangover, this will come up.
Is it the only article you'll get?
It's Peter Winkler and colleagues, and Peter Winkler is a resource everybody should know. He has wonderful books and materials that can be used for math circles just off the shelf when you're
Yeah,
looking.
here it is,
Look up
Peter
Peter
Winkler.
Winkler's
At Dartmouth.
brilliant.
Thank you, Dave, for mentioning this. Science, by the way, is published at the place where I work, the American Association for the Advancement of Science. Next slide, please. Extraordinary here that we saw a building which was just straight lines and triangles, and very expensive to build because the bathrooms and so forth are that shape. This building was very expensive because there are no straight lines in this building for various reasons I won't go into. And I want you to notice the dome is particularly interesting, the architect's drawing. Next slide. And if you go inside the building, they're looked straight up. You appreciate the dome even more. And this window has prisms in it. Okay, next slide. So that on the other wall, you'll always get a pattern of this type. Again, the mathematics is interesting. Next slide. If you understand how color is broken up, and you, that's it. Okay, next slide. Mazes, of course, are mathematically extremely interesting. There's a man at Stony Brook who's published a great deal on this. So if you put maze of Stony Brook into Google, this will come up. Okay, next slide, please. It shows how to make a simple maze. I've done that before, but just with the little right angle and the dots. Okay, next slide. The domes of Washington. Extraordinarily magnificent city that we have on the mall. Here's the Capitol dome. And when I first began giving tours, I just had people go out and put their hand right there from your seat to get this shape. So, physical, come on, put your hand up. Okay, great. And then rotate it so you get a sense of what a volume is. A lot of times we leave out the physical connection to mathematics. And then, next slide. So this is another dome. It's pretty well covered up. This is the magnificent Library of Congress. Next one. And that's the Natural History Museum, National Museum of Natural History. And next one. And there's the Jefferson Memorial. And you notice, again, if you put your hand up, you're now getting a completely different shape. So you have a different sense of what a volume is. And of course, the mathematics that you can do at every level is very, very interesting. There's a rotation, layers, cuts, circles, and so on. Next slide, please. And this was set up a couple of years ago by the Air and Space Museum. It's right in front of it. And it is, I have to get it in front of me, its scale, the solar system, is 1 to 10 billion, okay? And that's hard to imagine, but that means that you can see a great sense of our whole solar system by just going down to the next slide, please. So there's the sun, okay? That's how big the sun, they were able to make the sun in order to have the 9 planets through there. They're crystalline spheres. The rest, 2 minutes, perfect. Okay, next slide. And now we'll just cross the mall and go in the National Museum of Natural History and go into the room where the great Hope Diamond is and look at the magnificent gems in there. And they've set it up so that the mathematics is very clear on how crystals are formed, and as you know, they're very restricted, but these are actual photographs of crystals that have formed there, that they have in their collection. They have thousands of these, all different types. This happens to be pyrite. Okay, next slide. And these are the possible shapes, so this came directly from their museum display. And again, unless you're very familiar with crystals, you forget how much fun it is. And they have an exhibition of salt that's big enough for you to go inside, so you really get a sense of the geometry. Next slide. I just threw this in to show that we have things off the mall as well as on the mall. And the U.S. Naval Memorial, next slide please, is the largest grid map of the world. And you can walk all over it right there. So if you want a sense of the distortion that comes from making maps, there it is physically right in front of you. Next slide. Next slide after this. Okay, tensegrity. Next slide. This one is called Time and Technology. It's in front of the National Museum of History. And you can see the Washington Monument over here on the left. And this is a Mobius strip. It was the first funded piece of art by the federal government in a federal building. They did a bunch of other things. And it rotates. Definitely. Okay, next slide. We're getting near the end, and this is down at the National Academy of Sciences, which if you walk out here, you only have to go about 5-minute walk, and you'll be here at his Einstein statue. And Einstein is sitting on top of a map of 55% of the sky on the day that the memorial was dedicated, which means it's possible by computers to tell where the stars are in the sky.
I walked by Albert yesterday, and there's a big fence around the whole front yard of the National Academy. We couldn't get too close. We could see him, but you can't actually go up there, I think, unless it's different this morning than it was yesterday.
Okay, next slide. Well, great, next one. Okay, and it's not a very good slide, but the map that's showing all the stars and there's ours and so forth is explained. You couldn't get next to this either then. Dan?
No, I don't think so.
You don't think so? Okay, next slide. Okay, on the front of the building, oh, that's right, they're restoring the facade.
Yeah,
that's what's happening. So, I just realized that. Anyway, carved there in bronze, there are the great mathematicians that we like to talk about, such as Euclid. Okay, and you see he has a little triangle to keep him comfortable. Okay, and if you were able to go inside this building, you'd see one of the architectural wonders of the city. And when I first went in here, I could not believe this place actually existed, because there are many tons of free-hanging clouds up here. And the end result of this gigantic room at the National Academy is if somebody's playing the violin here, you can hear every note in the very back of the room. Similarly, if I'm sitting in the back of the room and I go, they can hear me. And so I wrote to the architect and got the architectural drawings, and it's because it's a cycloid. Okay, so it has no focal point. Okay, next slide. And now we're at the final place, or next to final place, at the Vietnam Memorial, which you may have already seen or certainly seen pictures of. And this picture is taken standing at the very bottom of the memorial, the top of which is at ground level, and looking straight east to the Washington Monument. Next slide. And this is taken at the point here is where the other picture was taken. So this is coming in this way and going out that way toward the memorial. Next slide. And people are always looking at this, and you can see how the names are on panels of the individuals who are known to have died during the Vietnam War. And the next slide, please. And this is an overall picture of it, showing its ground level on the right, and then it's a gash in the earth. And I took some middle school kids, elementary kids to this. And we had a dance instructor, and the dance instructor said to the kids, "How do you know how many names are there?" And I wrote this down so I wouldn't mix it up. And one girl noted that the names on each line was fixed, so suppose 1, 3, 5, like that. And that the number of lines varied on each panel in a very specific way. And one 9-year-old boy then just said, "Oh, well then I know how many there are." Good question. Very math circle kind of question. And what he had done in his head was, he says it's 2 triangles, so if you put them together, you have a rectangle. And therefore, since there's a certain number, that each column in the rectangle would have that fixed number. And so all he had to do was count the number in each column. And he determined that there were 58,000 9 years old. And when he was asked how he did it, he said that there was a really smart girl that knew how to do it. And had recognized the pattern. And so he just built on that. And there are, by the way, 58,132. So it's pretty incredible what kids can do. And one more slide, and we're now at the end of the mall at the Lincoln Memorial. Does anybody have any money with them? If you have a penny, this is engraved on the penny. And so is the statue of Lincoln, always visible right here on your penny. So it's a nice souvenir of the math in Washington. And it's nice to know how Lincoln felt about mathematics. He became a lawyer, as you may know, and then he said, "But I don't know what truth is." And so he took up his Euclid, and he read all 6 big books of Euclid, and he said, everybody must do that, and he read it every single night for the rest of whenever he could for the rest of his life. And if you go inside this building, next slide, there he is, and next slide. He then took a phrase directly up here when he says, that this is a proposition that all men are created equal. And the Gettysburg Address came directly from him. Okay, now that's the end of my math on the mall, but I want to just make a couple of comments about my colleagues, what they did. First of all, Glenn and Arnold Ross, the program that I've conducted with Dan Ullman here for the last 8 years was for middle grade mathematics teachers. But it was based on the premise that Arnold Ross always said, think deeply of simple things. And the other one is that people have asked about materials. For the final year, during the final year of our program, the middle grade teachers who were getting master's degrees from George Washington University in middle grade mathematics, a professional degree, they had to keep journals for the 3 years of the program. And the final year, they brought those all together and looked at the hard questions like, how do I learn to think like a mathematician? And then, how do I learn to think like a mathematician? And then they created papers, which have been published, 4 of them by the Washington Academy of Science, on how a teacher who normally teaches 4th and 5th grade is enabled to think like a mathematician. They would come together once a week and have a seminar, which they created. Okay? And then when the seminar was over, when the presentation was over, they spent an hour and a half just doing math problems together. And where did I get those problems that were appropriate for them? 100% of them came from Dick Stanley. And I don't know how you go about getting them. He created them when he was at Berkeley. And a typical problem would take 8 1.5-hour periods for the teachers to get through. So each year we did 2, maybe 3 of these problems, and there are 11 of the problems. One would be on rates, for example. And teachers would just work together, and that enabled them to go back to their classrooms and form that kind of attitude with their kids. That good problems are worth taking a lot of time to do.
So, I think we will find a few minutes for some questions for the panel and for some discussion amongst them. I'm particularly interested, Glenn Stevens mentioned that he brought some of the teacher circle activities into the classrooms during the classroom day with the teachers, if I understood correctly. How did he set that up? How did he get started with?
Actually, no, I wouldn't say we did. What we find is it's very, very hard to get into the classroom. I've definitely been in classrooms, but you can only do it in a one-shot deal. There was one example of a project I did with a teacher over a bit of an extended period of time, where we sort of measured the circumference of the Earth by comparing lengths of shadows on 2 different days, very carefully marked out. And that was a lot of fun, and the kids enjoyed it, and it was an opportunity for me to see the insides of a classroom. And that's kind of, it's hard though. I think it's very, very hard to do that. What we do more is work with teachers after school, and we do that in their classrooms, but not while students are there. It's very, very hard to get permission from principals and administrators for someone who's not actually a teacher to work in the schools for any kind of an extended period of time. And I do believe that only an extended period of time is likely to have a real impact. And so everything we do is focused on helping teachers do that. So the teachers are already there. And so our goal is to do that. By the way, one of the things that we're beginning to focus on now and realizing, and I'm sorry it takes us so long to figure these things out, but hearing you talk about the need for materials, that's finally become obvious to us that the most easiest thing that we can do for teachers is just produce materials. And so we are thinking about that. We've also discovered there are certain curricula that are particularly good at bringing problem-solving ideas and the kinds of ideas that we try to focus on into the classroom. And I hope I can advertise. I'll mention the CME curriculum. Excellent thing. Al Coco was one of the, I think probably the lead author. We work all the time with Al Coco in Boston, and I really love that curriculum. And so we're going to try in the future to connect what we do. Try to work in schools that already have that curriculum, so that the work we do after school becomes automatically connected with the work that they do during the day. And we've definitely seen the difference, by the way. If you connect to the curriculum that's being used in the school, there's a huge difference in the level of participation that teachers give.
Yes, Dan.
So I want to think a little bit about this idea of making better materials. We all want textbooks and materials that scintillate, but unfortunately they suck. So I proposed the foundation called Scintillates Not Sucks, which we could all start here together. And we're probably not the first gathering of smart math educators who think that we can do a lot better than what's out there. I am not so certain about that. I have a feeling that a good textbook needs to take into account the teacher, the student, the community, the culture, the classroom, the level of the kids, and every set of materials is working for some kids and not for most others. So I don't know that there is a solution to this, and I'd like to ask the panel, are there really just good materials and bad materials, and we should throw away the bad ones? If we all use the good ones, we'd all be better off? Is it as simple as that?
I don't think it's as simple as that. So, I'm sorry to say that. Step on you right there. I don't think it's as simple as that. I think that that there are good things and bad things about a number of different materials. And as a classroom teacher, I've always picked and chosen. Pick and choose. Take what I like from this book. Take what I like from that book. And I like this activity, but it's not quite right, so I'm going to write up my own version of that and just print that one out and give it to kids. And so I think that it's a matter of piecing together the pieces. I'm not saying this very well, but that's the components of taking bits and pieces from each of the different things. But I think that the number is in the Austin School District. Let me speak to that. When I was in the classroom, we were working with the Connected Mathematics program in the middle grades, which I liked a lot. And when I left to move to UT, within the next year or two, we went through textbook adoption, and CMP was out, and the Holt textbooks came in, and I hate the Holt textbooks. No offense to anyone. But it's very much, here's the problem, 3 pages of how to do, here's how to do the problem, 3 pages of practice, here's how to do the problem, 3 pages of practice. And so now those are the things that the teachers have in hand, because that's the stuff that's been adopted by the district. So although no single textbook, I think, will become the solution for everybody, I worry that some of the teachers in my district just don't have access or know about, or you're coming in brand new, you're a first-year teacher, and Holt's what you've got, then Holt's what you go to, and if they don't know about, haven't heard about CMP, then they don't know where to go for it. So it's a question of awareness too, I think, not just having one book that's going to solve all the problem.
And I think too, some of the textbooks have got guided problem solving in them, but I don't like guided problem solving. That's not what this is about. In my mind, it's thinking, and it's a kind of professional development that I think comes through math teacher circles. It's hard to teach specifically how to do this with students, to spend all day on one problem and be okay with that. And to me, that's the goal, perseverance. Will you stay with it? Will you continue to ask questions? Will you live in it? And I don't know that a lot of teachers have a comfort level in doing that or know how to do it. And so it's not in that curriculum. Okay, have them stay with it. Here's the guided problem-solving process. Make the problem simpler, and they think that's problem solving, and it helps, but I'm not sure that it's in the curriculum.
So I actually am part of a group that's called Escape from the Textbook. You guys have heard of it? And it's really about teachers who and math educators who don't want to have their curriculum dictated by a particular textbook. Having said that, we still need materials, and we share a lot of materials and ideas. I personally think there is a way to put something together that's really, good for everybody. It would have some flexibility into it, but it would have to kind of, incorporate a different philosophy about mathematics. Not a philosophy of, I can talk you into understanding this, which is what it does. I can lead you through these steps and everybody get it. Well, we know, in fact, it's experience and struggle that allows you to really get to understanding. And so that's part of the problem, is in the Holt books and stuff, is that also the Holt ones, the one I'm using anyhow, is way too symbolic based. So any kid who does not have really good access to symbolic language is gone. Automatically, and for struggling students, any kid who is doesn't have really strong numeracy skills is also automatically like, I can't use it at all. So I think occasionally I can get a problem out of it.
I have a general comment on this subject as well. In my Calculus 2 class I'm teaching this semester, we've switched over to the e-book, which is, in my opinion, the most ridiculous thing that we've ever done, because it turns their textbook, which was already not very good, into a Wikipedia page, which they just blank out completely if they look at it. But the way the company pushed it was that we had to, the instructors can now go through the e-book and we can put in our own comments on certain problems. We can actually, kind of electronically write in the margins so that everybody can see it. I don't like it. I've never done any of that stuff. I typically only use textbooks as a rough outline of things that I want to cover. It's not a question necessarily. It's just a comment about kind of another way that textbooks are going that I don't know if anybody else has the same feelings about them that I do.
I'll just make a comment as someone who taught for a number of years. And I just never could teach sort of sequentially exactly as a textbook told me I should, but I basically would use it sort of as a guide as to topics or I needed to cover as opposed to specific content. And it was a source of problems that I could get kids to practice with too. But, and so over the years, I built up an incredible collection of problems that I found places and that I wrote and so forth. And years ago, Dale Seymour and Creative Publications and Cuisenaire used to publish supplementary materials that were really excellent. And they were copy-readier materials that you could buy that were just books of problem solving and stuff. A bunch of these things have gone out of print. Some of the better ones have gone out of print. But if you can get hold of any of these or find old catalogs, I ended up, writing a couple of them and publishing them with Dale Seymour, but Dale Seymour got bought out by Pearson. They don't even bring my book on math history for middle school kids to the conventions. Nobody knows it's there. And it's a book that is copier ready for the teacher. It's background pages plus pages you can copy in the classroom that relates the history to the topics you're teaching. The other book that I was published by Cuisenaire was bought out by ETA, and they brought out their own parallel book to it, so they don't even take mine to the convention. You can still buy it, but if you don't know about it, you don't know to buy them in the Power Solid Manipulatives in the book to go with it. And so when I was talking with someone about it, someone who's a former editor who is now retired, what she said is Pearson isn't making money over the books that are copier ready for the teachers. If you buy a book and you can use it for your classroom, you buy it once. They only want to sell books that are consumable, so that every year the teachers have to buy more workbooks or more packets or more something that they're going to wear out, because that's where their money is. And if they don't have that, it's a whole bottom line issue. Pearson is an enormous multi-company conglomerate that bought out a whole bunch of different publishing companies, and eventually it's going to get down to just a couple publishing companies in terms of materials. I would love to see someone doing more writing of these materials and getting them out, but finding a publisher, unless you want to do your own publishing, may very well be a real problem with it.
So it looks like Mark and Bob have questions in order. Mark?
A comment on yours. I also had a book by Dale Seymour, which was brought out by Pearson, and now it's out of print. I wrote as the author to Pearson, and they gave me permission to post it on the web. And now it's on the web, and you can get it for free on the web. And I'm just wondering, that's something that maybe the Math Circle MSRI could do.
And in fact, we have a website where we're trying to index and collect lesson plans and materials for stuff. So certainly anything that you have the right to post on the web, if you want to post it on your own website, fine, cross-list it. Because the easier it is to find material, the better it is for everybody. So we should cross-list everything and try to dump everything into one source. And so I would like people to encourage people to put stuff on the NAMC website, on the lesson plan section or in the problem section. We're putting a lot of money into redoing the page and improving it, and we're really trying to put more materials.
Yeah, I'm specifically, this is greatly appreciated, but I'm specifically talking about how to print books.
Yeah.
The web gives a response to that if you can get permission from the author. And if you're the author,
I don't know
very
if
happy with this.
Okay, but I think you can still buy my book from Pearson. They just don't bother, letting you know.
Well, let's look at the other books
Yeah.
that are out of print.
Because some of the Mathlete problems that Carol Greenis and Rika Spungen wrote, that's my absolute favorite problem-solving book. And if that could be brought out on the web, that would be a wonderful source of problems.
Can you please say, for everybody, a lot of people are wondering what the name of the book is and your name also?
I'm Erica Bulich. I'm the person who spoke the first day about the Somerville Math Fund. But I wrote a book that is a hands-on geometry book, solid geometry book that goes with the power solids. So it's the manipulatives power solids. POWERSOL.
What's the title of the book?
I think it's called Explorations with Power Solids or something like that. If you type my name, Voolich, VOOLICH, and the word power solids into Google, it should come up. And the other book is a
It's
peek.
investigating with power solids.
Investigating with, because it was part of a series, Investigating with. Thank you very much. And the other book was a peek into math of the past. And it's basically taking topics that are in middle school, algebra, pre-algebra, and bringing in the history. And both of those books are copier ready, so there's pages for the teacher to copy, and there's pages that are background information for the teacher. So if you want to know something about Egyptian fractions and the history of fractions, it's there. And there's activities there that like with the Power Solids book, they said every Power Solids activity, every activity you put in the book has to do with Power Solids. But I put in my activities that I used to do on Hamiltonian circuits that I used to do workshops on, and I used to do in my classroom called Around the World on Hamiltonian Circuits. I started with the Power Solids counting, figuring out could you do a Hamiltonian circuit on the Power Solids, but then went to building with other manipulatives because I at least could start with that. So, I tried to bring it in as best I could with what I had to work with.
What was the name of Carol's book?
What?
Carol Dwenas, what was the name of her book?
She has a whole bunch of books. But the one, Mathletes, I think it's called. I'd have to look it up, but it was out of print, and one of the teachers who knew I was absolutely adored, the day she retired, she gave it to me that morning. She says, "Here, you can have my copy." I'd been lusting over it and had been using Xerox copies for years, and hers was falling apart, but now I have at least a copy that is there.
So we'll look at getting all these resources on the Math Circles website and then send an email out to the whole entire group once those are
In
up.
fact, we'll have a resource page for the workshop, and I'd encourage people to send me things to go with it. Maybe one more question or comment, Bob?
Just one quick thread. Emily made this comment, she used this phrase, culture of learning, and I'm really intrigued by that, so I know we're out of time. But I was curious, so the teachers who've experienced circles were talking about their circle experience and then being in the classroom. And I teach my circle of kids on Sundays, and I would kill to know what they look like Monday through Friday. So I wonder sort of how these things get connected, or are they just being in a different room with different people, how that changes everything. And that we should talk about.
I think we should thank the morning panel.